In last videos we already discussed about that energy stored in case of capacitor as well as electric density, and already we come to know about that force between the parallel wire. So already we solved some numericals related to these formulas. So now in today's class, so let me discuss about a redistribution of the charges. What's the mean of this redistribution of charges? For example, I will take the two body here, body A as well as body B. So on these two body having different kind of charges here, and these two body let me join with one wire here. So if these two bodies are connected between one wire means, so then in this situation that charges will moving from that higher potential to a lower potential. So while the charges are moving from that higher potential to a lower potential, up to what extent the charges will get flow here? So the charges are getting flow up to it attains a equilibrium position. So once it attains a equilibrium position means these two body will attain a common potential. If that bodies are getting common potential means I need to determine that what will be the mathematical expression for that common potential here. So in order to understand such thing, so first let me begins with the concept of redistribution of charges here. So we will understand about that redistribution of charges. So in case of that redistribution of charges, so first I will consider that two body here. One is body A. On that body A, Q1 amount of charges are present here and its potential is V1 here. And another body I will take it here. So this one is body B. So on that body B, Q2 amount of charges were present and its potential is V2 here. And its potential is V2 here. And so now these two bodies are getting connected by one thin wire here. If these two bodies are getting connected by one thin wire means, so that charges are flowing from that one body to other body, or in the sense from that higher potential to a lower potential here. So while that charges are transferring from that higher potential to a lower potential means up to what extent the charges are flowing here? Up to these bodies attains a equilibrium position. So in that situation, so charge will be remain same here. So total charge, so from the conservation of energy, from conservation of charge, total charge Q is equal to what? Q1 plus of Q2 here. So for example here 10 coulomb of charges are present, here 5 coulomb of charges are present. So that excess amount of charges will flow from that one body to other body. Let that after connecting, charge on the two bodies are Q1 dash and Q2 dash here. So from that conservation of the charge, total charge is conserved here. So it means that Q1 dash plus of Q2 dash is equal to what? Q1 plus of Q2 here. So let me consider here. So from the basic definition of capacitance, C is equal to Q by V. Q is equal to, shall I write it as a C into V here. So after connecting here, charges are flowing from a higher potential to a lower potential. After certain interval of time, these two body attains a common potential. Let V be the common potential. So Q1 dash means what? C1 into V here. After connecting, charges are flowing here. C2 into V. So before connecting, C1 and its potential is V1. Second body C2 and its potential is V2 here. Shall I take that V as a common here? C1 plus of C2, it is equal to C1 V1 plus of C2 V2. Okay. Then V is act as a common potential. So my interest is to determine that value of the common potential. So V is equal to what? C1 V1 plus of C2 V2 divided by C1 plus of C2. So this is the required expression for the common potential. So V is equal to what? C1 V1 plus of C2 V2 divided by C1 plus of C2. Shall I rewrite this equation in another form? C1 V1 is nothing but what? Q1 here, Q1 plus of C2 V2 is nothing but what? Q2 here. divided by C1 plus of C2. So this is also expression for the common potential. So in general I can say that in terms of words I can consider Q1 plus of Q2. So that is nothing but V is equal to common potential is equal to, so common potential. So it is equal to what? So Q1 plus of Q2 is nothing but what? So total charge divided by C1 plus of C2 is nothing but total capacitance. So what is the generalized formula I can say here? Common potential is equal to total charge divided by total potential here. So look at here, in that situation, so capacitance C is directly proportional to Q here. So after connecting, so new capacitance is C1 dash and its charge is Q1 dash. So new capacitance is C2 dash and its charge is Q2 dash. So if I take that ratio C1 dash divided by C2 dash, it is equal to Q1 dash into Q2 dash. So this is the required expression I can consider here. So now look at here, I will consider the two capacitors here. So initially these two capacitors having that potential V1 and V2 and its capacitance value is C1 and C2 and charge on these body is Q1 and Q2 I can consider here. If these two bodies are getting joined means charges are redistributed I said. So if the charges are getting redistributed means so there will be loss in energy here. So why that energy is getting lost here? That energy is getting lost just because of redistribution of the charge. So in case of that redistributing of the charges, energy is getting lost I said. If the energy is getting lost means I want to find out that how much energy is getting lost in case of redistribution of the charges. So in order to understand that energy loss in redistribution of charges, I will give that mathematical approach for that energy loss in case of redistribution of the charges. So already we got that expression for common potential here. So if these two bodies are getting connect means so charges are moving from that higher potential to a lower potential up to it attains a common potential. So equation for common potential, V is equal to C1 V1 plus of C2 V2 divided by C1 plus of C2, or one more equation is, so V is equal to what? Q1 plus of Q2 divided by C1 plus of C2. In case of that redistributing of charges, there will be a loss in energy. So let me find out that loss of energy in redistribution of charge. Loss of energy in redistribution of charge. Okay. So for that purpose, first I will consider the two capacitors here. So for example, this is one capacitor, its value is C1, its potential is V1 and charge is Q1 here. Let me take that another capacitance, its value is C2 and its potential is V2 and charge on it is Q2 here. So now these two bodies having that initial potential energy. So I will consider that initial potential energy of these two body here. So look at here, I will consider two capacitors here. These two capacitors having that value, consider capacitor, consider capacitors C1 and C2. Its potential is V1 and V2. So its potential is V1 and V2 and Q1 and Q2 be the charge on it. Charge on it. So now I will consider that then energy stored before connecting. So two capacitors I will consider that. So now I want to calculate that what will be the initial energy before connecting these two capacitors. Then initial energy store before connecting. So I am determining that energy loss. So energy loss means, so initial energy minus final energy. If I do like so, I will get that energy loss here. So for that purpose, first I will find out that what about that initial energy stored if these two capacitors are not connected here. So what is that mathematical expression for that energy stored in case of capacitor? So that energy stored in case of capacitor is half of CV square here. So three different forms are there. So just I will consider that half of C into V square. Why? Because these two capacitors later on I will connect in a parallel combination. So half of C1 V1 square initially. So first capacitors having that capacitance value is C1 and its potential is V1 plus of second one C2 into V2 square. So look at here. So this is that initial capacitance, initial energy stored. So of that two capacitors before connecting. So now let me consider that after connecting, after making connection. So after making connection means, so let me take that two capacitors here. These two capacitors are joined in this manner. Its capacitance value is C1, potential is V1, its value is C2 and its potential is V2 here. So again that charges are moving from that a higher potential to a lower potential here. Again that charges are moving from that higher potential to a lower potential means these two capacitor will attain a common potential. So first let me write that equation for common potential. So after making connection, these two capacitors will attain a common potential. So after making connection, common potential is so what is the expression for common potential? C1 V1 plus of C2 V2 divided by C1 plus of C2. So this is the required expression for the common potential. Then what about the final energy stored after connecting here? So final energy stored after connecting means after certain interval of time, potential of these two capacitors are V only. It attains a common potential. So now let me consider that final energy stored is. So final energy stored, U of F is equal to half of C1 into, what is the potential of first body? V square here plus of half of C2 into V square. It attains a common potential. So U of F is equal to, so which thing I need to take that common here? So V square, shall I take that common factor here? C1 plus of C2 into V square. Let me take this as a equation 3 here. Look at here, wherever V is there, so instead of V, shall I take that C1 V1 plus C2 V2 divided by C1 plus of C2 here? Is it right? So look at here. So I will take that. So I will substitute that equation 2 value in equation 3. So let me write that. Put equation 2 value in equation 3. Then that equation 3 becomes, so U of F is equal to, so U of F is equal to what? Half of C1 plus of C2 into V square means, so shall I take this one as a C1 V1 plus of C2 V2 divided by C1 plus of C2 whole square. V square is there. So one more step I need to simplify here. Half of C1 plus C2 whole square here. So C1 plus of C2 is there. One term will getting cancelled out here. So C1 V1 plus of C2 V2 whole square divided by C1 plus of C2 here. Hope you are understanding here. So C1 plus of C2 term is there. In denominator, C1 plus of C2 whole square. One term will getting cancelled out here. So this I will take it as a equation 4 here. Now I want to find out that loss of energy. Then loss of energy is, how to find out that loss of energy here? then loss of energy is, so delta of U is equal to initial energy minus of final energy. So let me subtract value, subtract that initial and final energy value. So what's that initial energy here? Half of C1 into V1 square plus of half of C2 into V2 square here minus of so look at here, what's that final energy here? Half of C1 V1 plus of C2 V2 whole square divided by C1 plus of C2. Final initial energy minus of final energy here. Let me simplify this equation. Delta of U is equal to, in this equation I will take half of 1 by 2 into C1 plus of C2. I will take it as a common factor here. Which thing I need to take common here? So look at here. So in that main equation, so I will take that. So delta of U is equal to 1 by 2 into 1 divided by C1 plus of C2. I will take it as a common factor here. So 1 by 2 C1 plus of C2 if I take common means, so this equation becomes C1 into V1 square. In denominator C1 plus of C2 is there. In numerator I will write it as a C1 plus of C2 here. Similarly plus of half I took it as a common here. In denominator C1 plus of C2 is there. So in numerator I need to write that C1 plus of C2 here. So hope you are understanding here. Minus of 1 by 2 C1 plus C2. Already I took it as a common here. So let me write it here. C1 V1 plus of C2 V2 whole square. So hope you are understanding here. So from this equation just I took that half of, so 1 by 2 into 1 by C1 plus C2 I took it as a common here. So 1 by 2 is common. C1 V1 square. So in denominator C1 plus C2 is there. Just I will make that. In numerator I will multiply by that C1 plus of C2. Here also same. In denominator C1 plus C2 is there. So this term will become as C1 V1 plus of C2 into V2 whole square. So now look at here. 1 by 2 into 1 divided by C1 plus of C2. Let me simplify this equation. C1 V1 square into C1. C1 into C1. C1 square into V1 square. Plus of C1 into C2 into V1 square. Plus of C2 V2 square into C1. C1 into C2 into V2 square. Just I am multiplying here. Plus of C2 into V2 square into C2. C2 into C2. C2 square into V2 square. Hope you are understanding here. So look at here. C1 plus of C2, sorry, C1 into V1 plus of C2 into V2. So this is in the form of A plus B whole square here. So A square plus B square plus 2AB. So outside the bracket here. So if I remove this bracket means A square minus A square means C1 square into V1 square. A square plus B square plus into minus, again minus here. Minus of C2 square into V2 square plus 2AB plus into minus, again minus 2 times of A means C1 V1, B means C2 into V2. So hope you are understanding this equation. So now in this equation, so just I will cancel out that C1 V1 square minus C1 V1 square. Plus C2 V2 square minus C2 V2 square. I will make cancel out here. So now look at here. Delta of U is equal to what? Delta of U is equal to half of 1 divided by C1 plus of C2. So in remaining equation, here C1 into C2, here C1 into C2, and here C1 into C2 term is there. Shall I take that C1 into C2 term as a common here? So if I take that common here, C1 into C2. Now look at here. So if I take that C1 into C2 means which term is remains here? V1 square here in this equation plus of V2 square. Next in one more equation 2 term is there, V1 into V2 minus of 2 times of V1 into V2. I got that final equation. V1 square plus V2 square minus 2 times of V1 into V2. Shall I rearrange this equation as a minus B whole square form? If I do like so, finally I will get that equation for energy loss. So delta of U is equal to, so I will write that equation here. So hope you are understanding here. Just I will rub out here. Okay. So look at here. So delta of U is equal to 1 by 2. As I said here, in this equation C1 and C2, C1 into C2 is a common, C1 into C2, if I take that common here, look at here, so this is in the form of A minus B whole square, V1 minus of V2 whole square. So this will be the required expression for energy loss in case of a redistribution of the charges. So look at here, delta of U is equal to 1 by 2 C1 into C2 divided by C1 plus of C2 V1 minus of V2 of whole square. So this equation is applicable only when, so look at here, certain conditions are there. So here I took that expression for energy loss and common potential and all the things. So in that situation, I took that two capacitors here. These two capacitors are arranged in such a manner that, for example, capacitor consists of two plates here. So if I arrange like this, these two capacitor attains a common potential, I said. So this equation is applicable when negative terminal of one plate is connected to negative terminal of the other plate and positive terminal of one plate is connected to positive terminal of the other plate. Then the equation for energy loss and then equation for common potential, C1 V1 plus of C2 V2 divided by C1 plus of C2. So in this condition, these two equation I need to use. Suppose if you connect that capacitors in another way, negative plate of first capacitor is connected to positive plate of the other capacitor, or positive plate of one capacitor is connected to negative plate of the other capacitor. In this situation, what will be the equation for energy loss? So that is delta of U is equal to half of C1 into C2 divided by C1 plus of C2. Just I will make that V1 plus of V2 whole square. So just a small change here, V1 plus of V2 whole square. If these initial potential, so V1 is equal to V2, is there any kind of energy loss here? If V1 is equal to V2 means there is no energy loss here, so it becomes as a 0. In case of that, this situation here, energy loss is 0 here. So now what about the common potential in this situation? V is equal to what? C1 V1 minus of C2 V2 divided by C1 plus of C2. So this is the required equation for energy loss and common potential for this case, and energy loss and common potential for these kind of arrangement here. So hope you are understanding these things. We'll move next thing related to these capacitance. So for example, so I am having that n number of identical liquid drops I will consider here. These liquid drops having that charge Q amount here. So look at here. So now I will consider that n number of liquid drops and these drops having that charge Q amount here, and its potential is V here, and radius of each small drop is smaller I will consider. So look at here, consider n identical liquid drop n identical liquid drop. So consider n identical liquid drop of radius r. Its radius is r, charge is small q, capacitance is small c, and potential is V here, small v, potential is V, and energy is U, and surface charge density is sigma. Then these small identical drops I will combine, it forms a bigger drop here. So for example, these are all n number of identical drops here. So these n number of drops having that, each drop having that q amount of charge here, and each drop having that radius r. So it forms a bigger drop. Instead of taking that n number, so if I join these drop, it forms a bigger drop. This bigger drop having that charge q, this bigger drop having that potential C dash, sorry, capacitance C dash, and this bigger drop having that potential V dash, and this bigger drop having that potential energy is U dash, and this bigger drop having that surface charge density sigma dash. Now let me find out that what is the charge on the bigger drop, capacitance of the bigger drop, potential of the bigger drop, energy of the bigger drop, and surface charge density of the bigger drop. So in order to calculate that, first I will consider that charge on bigger drop. Charge on big drop. So charge on big drop is equal to, so capital Q means charge on big drop, it is equal to n into charge on the small drop. What is that expression here? Charge on big drop is equal to, so capital Q indicates that charge on the big drop, it is equal to n into charge on the small drop. So now another one, I want to find out that radius of the bigger drop. So let r be the radius of the bigger drop and small r be the radius of that these small drops here. So next I will take that radius of bigger drop. Let me find out that radius of big drop here. So radius of big drop is nothing but what? R here. So R is equal to what? So look at here. So here that n number of identical drops, if I join means I will get that single drop. So let me find out that volume of that, volume of these small drop is equal to volume of the bigger drop. Why? Because volume is remains same here. So volume is remains same means n into 4 by 3. So volume of that small drop n into 4 by 3 into pi r cube, it is equal to volume of the small drops is equal to volume of the bigger drop, 4 by 3 pi into r cube. 4 by 3 pi will getting cancel out here. N into r cube is equal to what? R cube. R is equal to what? Shall I write that R is equal to n to the power of 1 by 3 into r here. So then what will be the expression for that radius of bigger drop here? Radius of bigger drop is equal to n to the power of 1 by 3, where n indicates that number of liquid drops here. So R is equal to n to the power of 1 by 3 into radius of the small drop. So radius of the bigger drop is equal to n to the power of 1 by 3 into radius of the small drop here. Next I will take that capacitance of the bigger drop. Capacitance of big drop. So look at here. So C dash is equal to what I need to find out here. So let me consider that basic definition for that capacitance. So C dash is equal to what? So C dash is equal to Q dash. So first let me find out that Q dash. So C is equal to Q by V here. Okay. First look at here. So in case of this, Q dash is nothing but what? Or Q dash, or Q is equal to what? N into Q here. Q dash is equal to N into Q. So volume of the bigger drop. So I will consider so that. So first let me find out that potential here. Then I will consider that, or let it be. So 1 second, sorry. We'll consider that capacitance of the big drop. Sorry. C dash is equal to what? So capacitance of bigger drop. So it is a spherical conductor. So what is the mathematical expression for capacitance of a isolated spherical conductor? So 4 pi epsilon naught into r. So look at here, what is that expression here? C dash is equal to 4 pi epsilon naught into r here. What's the value of r here? So look at here. So look at here. So C dash is equal to what? So 4 pi epsilon naught. 4 pi epsilon naught, where r is nothing but what? Capital R is equal to n to the power of 1 by 3 into small r. So I shall rearrange here. So that is n to the power of 1 by 3 into 4 pi epsilon naught into r. So 4 pi epsilon naught into r means capacitance of the small drop. So C dash is equal to n to the power of 1 by 3 into C here. What is that capacitance of bigger drop here? So C dash is equal to n to the power of 1 by 3 into capacitance of small drop. So capacitance of bigger drop is equal to n to the power of 1 by 3 into capacitance of the smaller drop. So next I will consider that potential of the bigger drop. Potential of the big drop. So V dash is equal to what? I need to find out. So V dash is equal to what? Q dash divided by C dash. Q dash or capital Q is nothing but what? N into Q here. C dash is nothing but what? C dash is nothing but a n to the power of 1 by 3 into C here. So let me simplify this equation. N to the power of 1 is there. So if it goes to numerator, n to the power of 1 minus of 1 by 3 Q divided by C here. So look at n to the power of 1 minus of 1 by 3. So that is nothing but, so n to the power of 2 by 3 into Q by C is nothing but what? Potential of the smaller drop. So V dash is equal to what? So V dash is equal to n to the power of 2 by 3 into V here. So potential of the bigger drop is equal to n to the power of 2 by 3 into potential of the smaller drop. So potential of bigger drop is n to the power of 2 by 3 into potential of the smaller drop here. So similarly, energy of the bigger drop, so that is potential energy. Energy of big drop. So energy of the big drop is nothing but what? U dash. So U dash is equal to what? So let me find out that. So energy stored in case of capacitor, Q square divided by 2 times of C dash here. Q square is nothing but what? N square into small q. Capital Q is nothing but what? N into Q here. 2 times of C dash is nothing but what? So C dash is nothing but what? So N to the power of 1 by 3 into C. Let me rearrange this equation. So n to the power of 2 minus of 1 by 3 into Q square divided by 2 times of C here. So 3 into 2, 6 minus 1, 5. So U dash is equal to n to the power of 5 by 3 into Q square divided by 2 times of C means potential of the smaller drop. So what is the mathematical expression? I get it here. Potential of the bigger drop is equal to what? Potential of bigger drop is equal to n to the power of 5 by 3 into potential of the smaller drop. So potential of bigger drop is n to the power of 5 by 3 into potential of the smaller drop here. So let me find out that last one, surface charge density. So let me list out here. So look at here. I got that charge on the bigger drop, radius of the big drop, capacitance of the big drop and as well as potential of the big drop and energy of the bigger drop. So look at here. So for bigger drop, so first I will consider that charge on big drop. Charge on big drop, what is that answer? Q is equal to, capital Q is equal to N into Q. Second one, radius of big drop. Radius of big drop, R is equal to n to the power of 1 by 3 into radius of the small drop. Next one, capacitance of big drop, C dash is equal to n to the power of 1 by 3 into capacitance of small drop. And next one, potential of the bigger drop, potential of bigger drop, V dash is equal to n to the power of what, 2 by 3 into potential of the small drop. Next one, energy of big drop, energy of big drop, U dash is equal to n to the power of 5 by 3 into potential of the, energy of the bigger drop is equal to n to the power of 5 by 3 into energy of the small drop. So last one is surface charge density. So what about the charge density of bigger drop here? So look at here. So surface charge density of bigger drop I need to find out. So what is the connecting formula? So surface charge density, it is the ratio of charge per unit area. So area means pi r square here. So look at here, Q is nothing but what, n into Q here, 4 into pi, r square is nothing but what, r is nothing but what, so n to the power of 1 by 3 into r whole square. So sigma dash is equal to what, n into Q, 4 pi, so n to the power of 2 by 3 into r square, or sigma dash is equal to what, n into Q, 4 pi r square into n to the power of 2 by 3. So sigma dash is equal to n to the power of 1 minus of 2 by 3 into Q divided by 4 pi r square. Q divided by 4 pi r square means, so surface charge density of the small drop. So sigma dash is equal to what? So 3 minus of 2. So that is 1 here. So n to the power of 1 by 3 into Q divided by 4 pi r square means surface charge density of the small drop. So surface charge density of bigger drop is nothing but what? Surface charge density of bigger drop is equal to what? N to the power of 1 by 3 into surface charge density of the small drop. So hope you are understanding these things. So in next class we will solve some numericals related to common potential, energy loss in case of the capacitor, as well as for n number of identical drops. So hope you are understanding these things.